So I hope my internet will not uh, uh, interrupt the lecture today, but today we'll move on to continue to talk about the Internet Protocol version 4. Remember that there is two versions for the Internet, right? Version 4 and version 6. Maybe we'll come to talk about version 6 at the end of the class, but we'll continue. So
Last week,
uh, we um, um, we were talking, or in the last lecture, I meant, we were talking about the IB and classes, how classes work, how classes are created. And the old way we have the classful, and then the new one, the new technique is the slashed notation or the cider notation, where you could have subnetting and supernetting, and this is a very important information to know. All right, it's imported everywhere you go. If you want to do cloud computing, you have to know it. If you need to do security, you have to know it. If you need to do basic network configuration, you have to know it. So make sure, and we covered a lot of examples, and I hope that you understand it very well. All right. So today we'll explain to you how the Internet Protocol work from inside. So what's the protocol? All right. So in simple words, if somebody could tell me what's a protocol, what is a protocol? The word protocol, what does it mean?
It's a way of device how you can talk with each other.
It's
like a computer.
It's rules, right? Rules. It's like a map, right? Map. All right, that's a protocol, right? There is a protocol how you talk to your parents. There's a protocol how to talk to your professors. There's a protocol how to, for example, talk to the president, or when you visit the White House. You know how to get in, how to have a distance. There's a protocols for everything, right? The same thing in here, like these two computers are communicating there, so there is a protocol there, right? Set up. So that's what we are talking about. So we're gonna explain the general idea behind the IP protocol and the position of IP in the TCP IP protocol. So this is which layer? This one, layer 3, right? All right, and then we'll show the general format for the IP4. And in here, the format, you don't have to memorize it. You have to know it, but you don't have to memorize it. And you will understand why we use this protocol, how things work together. So this is a very good example to understand any other protocol. So if you comprehend how protocols work, how they are built, number one, when you read any other protocol, you'll be able to understand it. And number two, you will be able to write your own protocols. And number three, you will be able to connect the dots. And that's the whole point of this. Again, the point in here, you have to understand how it works, but you don't have to memorize how it works, because there is map for you, given to you, if you need to interpret things. All right. Then we discuss the fragmentation and reassembly of the datagrams. So usually, because of the physical layer, has a limitation for the size of the datagram. So if there is a big chunk of data coming from the higher layers, they will not be able to go through the tunnel. All right, what you have to do, you have to fragment it. All right, and then the fragments will travel by itself and they will meet at the destination. Right, so that's what will happen. Think about, like in the application layer, that you're sending a huge zip file, huge. So this zip file will not fit in one fragment, right? It will not fit in one frame, right? So it will be divided. So we're gonna do fragmentation, and it will go all the way to the destination. And at the destination, what we do there assembly, as simple as that. All right. Then we discuss several options that can be in the IP4 datagram and their applications. What are these options and what they are for? Map. And then we show how checksum, okay, checksum to check for errors, right? That's for errors, right? So how checksum work, to check if there is an error in the frame, and how is it calculated. And then after that, this chapter talk about IP over ATM, which I'm not going to talk about, and then show simplified version of IP packages, and given maybe this I'm not going to talk about. All right. So that's what we will be talking in the first section of this class, right? So Internet Protocol IP, the IP, it's a transmission mechanism, all right, used by the stack TCP/IP protocol. Remember when we say TCP/IP, it's what? It's a stack. What does it mean, stack? It's like a whole system that combines many protocols in different layers. All right. So why we call it TCP/IP? Because these are the most important protocols used in this stack. All right. You could call it anything. You could call it Internet Protocol, for example, because it's used by Internet. You could call it Shakur Protocol. You could call it anything. They picked the most important protocol used, and they named the stack after it. So TCP runs in layer 3. TCP lies in layer 3, and this TCP runs in layer 4, and IP runs in layer 3, right? In the network layer, and this is in the transport layer. It's a very important also to remember that, you know, the OSI reference model. Remember that we start with the physical, right? Then after that we have the data link layer. Then we have the network, right? Okay, then we have the transport. Okay. Then after that we have like like these, we could call them the application layer, right? So 1, 2, this is layer number 3, and this layer number 4, right? And here we'll see IP protocol, for example, right? And here we'll see what? TCP. Okay, we'll see UDP protocol, which we'll cover later in different, and many other protocols that will be covered in this section. All right. So we'll talk about. So listen. Oh, it's in here. Actually, I did not have to draw it. It's in here. So as you see in here, we have in the physical layer, as you see, physical layer and data link layer, we have the underlying LAN and WAN technology. All right. What is example for a WAN technology or for a LAN technology? Anybody could give me an example for a LAN technology? Say that again.
A small network like offices.
No, give me a name for a technology used in the LAN.
Ethernet.
Ethernet, exactly.
Yeah, like Ethernet.
Ethernet, or okay, token bus, token ring. All of these are technology used in the LAN. Give me example for a WAN technology.
Router or
Like ATM,
phone.
Okay, SDL. There is multiple protocols used in the WAN technology. Okay. Anyways, this is like the bottom layers, 2 layers, right? Today we are talking about the network layer. Network layer is like layer number 3, as you know. And in the TCP/IP stack, we have multiple protocols running on the layer 3 for different functions. The major one is the IP protocol, which we're going to talk about in this section. Then we're going to talk about ARP. We'll talk about maybe next lecture about the ICMP and the IGMP. All of these are running where? Running on that network layer. All right. Then you go to the transport layer. There is the famous one, the TCP. That's why we call it IP. All right. IP, TCP, protocol stack, right? And we picked this, and we picked this, and we named it after that, right? And there is the UDP, okay, and there is the SCTP for streaming. All right. So remember also last time we explained about the protocols could be connection oriented or connectionals. You agree? So TCP is a connection oriented. It's like the phone system. UDP is connectionless. How about IP?
Connectionless.
It's a connectionless. Okay, it's like a mail is connectionless. So and then here in IP, what we talk about here, we talk about frames. Here we talk about datagrams. Datagrams. Okay. So remember that we have like a data like this. We have a header, and we have the data. Okay, data in here, and this data coming from from the transport layer. So we call it a datagram. So packets in the network internet layer are also called datagrams. So we call them packets, or we could call them datagram. These datagrams are variable length. That means they are not fixed. All right. Remember last time also we made a differentiation between something called a frame. What is the other word? Remember? Cell. Remember the cell? Like in ATM. So the cell is a fixed length, which is 52 octets or 52 bytes, but this is a variable. This has a minimum, okay, and has a maximum. Okay, so it's a range. All right, minimum and maximum. So in IP, we are using a frame. All right, and the datagram is a variable length, so the length is a variable. Okay, and it has two parts. What are the two parts? Okay, header and the data. Okay, two parts, the header and the data. Okay, it's a header in here and the data. So the header, it ranges between 20, that's the minimum, and up to 60 bytes, that's the maximum. All right, and that contains information essential for the routing. All right, it will have many. That's what we will be studying today, the information in the header. What are the information in the header? All right, and the header is like the map. It's like the brain of the packet. So for example, the header will have the source address, source IP address, and the destination IP address. So you know where it's coming from, where it's going to. You agree? All right, and it has many other information. This is like the map, how the data, how the frame will be moving. All right. All right. So the header, it will be, if it is 20 bytes. If it's a 20 bytes, the minimum. So the byte is 8. Uh, uh, um, you know, the 20 bytes. So usually it will be divided like 4 plus 4 plus 4 plus 4 plus 4. So 4 times 5, how much? 20, right? All right. So each one will have 32 bits, like 4 bytes, 32 bits, right? Okay, 32 bits, right? All right. So that's how we will take a look at that. So let's take a look. Maybe we'll see it in a second. Okay. So we'll take a look about the format of the datagram packet and some example. We'll take some examples. Here we go. So that's the IP datagram. We have a header. The size of the header is 20 to 60 bytes. Minimum 60 bytes and maximum 60 bytes. All right. The whole datagram is between 20 bytes. That means the data there is no data, and 64K. So this number 65532 is like 64K. You agree? Right? That's a 64K, the whole thing. That's the IP datagram. So in here, what we have in here in the data, we have a data coming from where? From the upper layer, which is the TCP. You agree? All right. Then we have the header. So let's take a look at the header. Here we go. That's the header. Okay. So as I said, the way we lay it out, like each line has 4 bytes. 4 bytes means 32 bits from 0 to 32. So this is like 4 bytes plus 4 bytes plus 4 bytes plus 4 bytes plus 4 bytes. All right. How much these? 4 times 5, how much? 20 bytes. And remember, we said the minimum is 20. And also we could have another 40 bytes, which is like an optional for other function, right? So we'll take a look later at the options, but these are the information that we have in each header. All right, let's start with the most easy one. So the easy one is the destination IP address. So where is the destination IP address? What is the size of IP4 address? 32 bits. It will fit the whole line here, 32 bits, from 0 to 32. And the other obvious information we have in here is the source address, which is another 32 bits. All right. Now there's other information that we need to take a look. So in here, version. Okay, here is the version, right? There is a version in here. What is the version? The version 8. Okay, let's take a look at them one by one. Let's take a look at them one by one. So the first one in here is the version, and it's 4 bits. So how many versions so far we have in IP?
So
2, either version 4 or 6. All right. So this 4-bit field defines the version of the IP protocol. Okay. So currently, again, we have like version 4, and either it will be version 4, all right, or version 6. There's no other option. All right. So this will tell you what version, okay, is available there. So and this will be processed every time the frame or the packet received. So all the fields must be interpreted as specified in the 4th version. So if you have 4 in here, then the layout of the rest of the information will be different than if you have 6 in here. The IP header for IP6 is completely different than how it looks for IP4. So this will help each node receives this header to interpret it. Okay, we'll know it's a version 4. Then, so in here we have header length, another 4 bits. So what we have in here, okay, what we do in here, it will tell you the length of the datagram header. Why we need this? Because we said the header could be 20 to 60. So we need to know how much we expect next. Is it going to be 20, or is it going to be 40, or going to be 50, or going to be 65? So this in here, it will tell you how much, what is the size of the header. It's like a map. It's like a map. All right. So this field is needed because the length of the header, again, it's in multiples of 4 bytes. All right. So it could be like 4. It could be 20 up to here. It could 20 bytes. It could be 24. It could be 28. It could be 32, up to 60 bytes. Right. All right. So it's in here. It's so if the field in here, if the value in here is 5. So what is the length of the header? So 5 times 4 equals 20. All right. If the field in here is 4, what does it tell you? What does that tell you?
the size.
16. So what does that mean? The packet means the packet is corrupted, because the minimum it could be how much? 20.
20, yeah.
20. So when a router receives a header and says it says 4 here, it will throw it out. It's like a corrupted, right? The minimum could be 5, right? You see, it's like a map. That's what I'm trying to tell you. It's like a rules that you have to learn, and that's what the machines are doing. When they're receiving the packet, they're reading it, interpreting it, doing an action according to the data. All right? Okay, so let me ask you a question. What is the maximum value we could have in here? So we know the maximum, the size is 60 bytes, and we know whatever value we have to multiply it by 4. So what's the maximum value to give you 60? 15. 15 times 4 will give you 60. All right. All right. So just that's what I need you. I need you to just to think this way. How you could read this. So this is the version. There's 2 options, and here the length and the values is between 5 and 15. If it's above 15, then it's a corrupted frame. If it's less than 5, then it's corrupted frame. And that will tell you how many data you have in the header. Clear? Okay, it's like a map. You're learning. Let's go to the next one. Surface type. Okay, and there's 8 bits in here. All right. So in here, in the surface type, or they call it TOS, or type of the surface, it defines the datagram should handle. So um, there is different surface levels. That could be low delay, high throughput, etc. Different ones. Okay, and there is a map for it. So in here, you take a look in here. So so remember there's 8 bits, right? So these are the 8 bits. 2 are not used. So how much we have to check? The code point in the first, the code point in the first um, um, the code point in the first section in here, right? So I'm sure there's a map for it. So let's look for the map, all right? So in here, all right, so if the 3 right bits are 0, 0, 0, then this will tell you the precedence interpretation, all right? So when the 3 rightmost bits are zeros, the 3 left, and here the 3 left uh, um, um, bits are interpreted the same as the precedence bits in the surface type, all right? And the precedence defines 8 levels. There is 8 levels. So 8 levels, that means, because in here, what is the range? From 0 to 3 to power 2. That means 0 to 7. How many levels we have? 8 levels. All right. So that will give different precedence or priority for the frame. And when do we need this data? When there is congestion in the network. When we have congestion in the network, sometimes we have to throw some of the packages away, right? When there's congestion. So what we do when there's congestion, okay, we look at the priority. So the packets that have higher priority we keep. That if we have to delete or throw away some of the packets, then we throw the ones have the lower precedence, right? So that's for the precedence interpretation as you see in here. So in the router, again in the router, when the router receives and there's a congestion in the router, traffic, it has to throw some packets away. I mean, just it's not functioning. So it takes a look at the precedence in here, and of course, the ones with 0 precedence could be thrown away. The ones for 7 will stay there. All right. So this is when the first 3 bits are 0, then it will interpret for you the precedence. And the other option, if the first one is 0, the first 2 is 1, 1, and then the first 2 is 0, 1. So this will give you a differential surface interpretation. All right, so we'll give you differential surface interpretation. All right, so the 6-bit surfaces, and that's what the map for it in here. Let's take a look in here. So if you have, like in here, the category 1, 0 regardless what is the value, then this is internet. 1, 1 in here, this will be local, and 0, 1, this is a temporary or experimental. This temporary or experimental. All right. So again, it's like a map that, and again, you don't have to memorize that. You have to understand it. So for example, in the exam, if I need to ask a question, I will give you all this information. Okay, just you have to understand it, all right, how it works. All right, so the first category contains like 24 surface types in here. Why 24? Because how many we have in here? So in here, 1, 2, 3, 4, 5. All right, 5. Okay. Okay, so this and the second and the third each have contain 16. All right. All right. So this is to control the performance of the network. All right. So let's go back. So what we have covered so far, we covered this, right? We covered this, we covered this, we covered this. Now in here, what we have in here, the total length, all right? Total length of what? Of the real data. Okay, the total things of the real data. In here, what does it in here give you in this field? The length of the header. Here will give you the length of everything. So how many bits we have? 16. So 2 to the power 16, how much? 64K, which is the one in here. All right. So the maximum size of the whole packet is 2 to the power 16, which equals to 64K. If I need to know how much is the size of the data, what should I do? Subtract this from this. This is the size of the header, and this is the size of the whole datagram. Then I will know how much is the data. You agree? All right. So let's go forward in here. So the total length field defines the total length of the datagram, including the header. All right. So it's like this. So you have in here, okay, you have data, which is like if the data less than 64 bytes, we have to add a padding, all right, and the minimum length should be 46. If it's less than 46, we have to add a padding. All right. So all right, it's clear. I mean, now we'll be able to know what's the size of the header, what's the size of the packet, and what's the size of the real data. All right. All right. So all right. So what else? What more data that we have to deal with? Let's go back in here. Okay. Oops. Here. So now we know the total length of the data. Now let's take a look at the identification. What is identification in here? So this field is used in a fragmentation. It's used when we do fragmentation. Okay, we'll take a look at that. Then we have flags, which is 3 bits. This field is used in a fragmentation. So this and this are used when you have fragmentation. Again, why we need to have fragmentation? When the data is bigger than the size supported by the below layer, we have to divide the data into fragments. And also in here, fragmentation offset, which is 13 bits. So the whole line in here is used for fragmentation. Okay. Then we come to time to live, and I think we explained that before. What is time to live? Anybody remember? When the data travel from one network to one network, all right, so there is a possibility that you have a lost of frame or a stray frame that, because, the routers keep changing, the data keep changing. So if we don't have time to live, this packet will keep circulating the whole network, will keep circulating from one network. So think about having like a million or billion like these packets who are stray, lost. What will happen to the network? Will get congested for no reason, traffic for no reason. So what we do in here, we calculate what is twice as the distance. So if this is the source, and between the source and the destination there is, like, let's say 8 routers. So we'll make it like 16 time to live. All right, time to live, right? So it starts with 16. When it goes to the network, becomes 15. When it moves to the next network, becomes 14. So every time it moves, it will be decreased. If it goes to 0, what will happen to this packet? Will be discarded. Okay, it will be discarded. So this way we protect our network from congestion. All right. and that's exactly what is the time lived. Okay, so this field mostly used to control the maximum number of hops or routers visited by the datagram. All right, so when the source host sends the datagram again, it stores a number in this field, and this value is approximately twice or 2 times as the maximum number of routers between the two hosts, the source and the destination. All right, you know that the routing table could get corrupted, and the packets could lost their way. So there is no reason to keep these packets flying in the network, moving from one network to network, and consuming the bandwidth, and finally they will not find their destination. So this is a very important feature that we have. Moving on, then we have the protocol, which is in 8 bits. All right, so what does this tell us? Okay, tell us what is the upper layer protocol. Let's go back a little bit, or let me go forward. Maybe I have it in the forward. Here you go. So you are in here, okay, and the packet is coming from up, right? From somewhere up. So is it coming from a TCP, or is it coming from UDP, or coming from different protocol? So this field, okay, this field will tell you what exactly the, okay, so in here, that's the protocols. So if this field is 0, then the upper layer is ICMP. If it's 2, then it's IGMP. If it's 6, then it's TCP. If it's 17, then it's UDP. If 89, then it's OSPF, which is a routing protocol, right? So this way you will be able to know what is the protocol coming from. So let me go back, see if we have covered everything in that in here. Let's take a look in here. So we know what is the version, either 4 and 6. We know what is the header length. It will be between 20 and 60. So the minimum value we have in here 5. The maximum value is 15. You agree? Then the surface type, okay, and there is 8 bits to determine that. Then we have the total length of the packet. All right, the maximum length, it should be 64K. If I need to know the real data, I subtract the header length from this value, I will know it. And then I have the identification, 16 bits, and the flag 3 bits, and fragment offset. All of this line is used for a fragmentation. We'll talk about it later. Then we explained about the time to live, okay, which is like a value that keep decreasing as we move forward. Then the protocol that tell me what is the upper layer protocol. Is it TCP? Is it UDP? Is it OSPF? What it is. And then after that, we have the header checksum, which calculates a value for the integrity of the whole packet. Okay, the checksum, okay, is it's a concept that is calculating, and we'll talk about it. All right, then you have the source IP address, and you have the destination IP address. All right, so that's what is in this header. That's what is in this header. As simple as that. All right, as simple as that. All right. Um, all right. So moving forward, okay, let's take a look what is next. All right, let's take a few problems. All right, and that's where I get you in the exams, right? That will show your understanding. So, in here, an IP packet has arrived with the first 8 bits. So these are the first 8 bits. So what are the first eight bits? Let's go back in here. Okay, the first 8 bits. Oh, the first 8 bits. What does tell you the first 8 bits? The first 4 will give you the version, and the next 4 will give you the length. All right. So okay. So let's take a look. Let's take a look again. Okay. So let's divide it into. So what's the value in here? This is the value is 2. All right. And what's the value in here? 4.
64.
4. So what does it say in here? It tells you what is the version of IP. So the IP version is 4, correct? So what is the next 4? What does it tell you? The length of the header. So how much is the length of the header? 2 times 4 equals 10, right? So what you concluded from this packet?
That
It's what?
is corrupt.
It's corrupted because the minimum here we could have 5. All right. So just reading, okay, reading the data in binary, you will be able to understand that it's IP version 4, and it says the length of the header is only 10 bytes, which is impossible. All right. So there is an error in this packet. The 4 leftmost bits, which is in here, show the version which is the correct. The next 4 bits, which is in here, shows the wrong header, which is 2 times 4, 8. I'm sorry, 2 times 4, 8, not 10. All right. The minimum number of bytes in the header must be 20. The packet has been corrupted in transmission. So what do you do with it? Trash it. That's what will the translation do it. Let's take another example. An IP packet, the value of header length is this. So what is this value? 2 to the power how much? 3, which is how much? 8.
8.
That means the length how much? 8 times 4, which equals 32. So the header size is 32. So how many lines we have? 32 plus 32 plus 32 plus 32 plus 32. This is 20. Okay, right? This is 20. Plus 4, 24. Plus 4, 28. Plus 4 will be 30. So how many lines we'll have? 1, 2, 3, 4, 5, 6, 7, 8. Right? When you go back in here, let's go back to the break. Okay. So we'll have 1, 2, 3, 4, 5, and another 3 lines in the options. All right. So that is the total. All right. So the first 20 bytes are the base header. So in here to here, this are 20, and the next, 12 are the options header. You see, giving you just bits, you'll be able to read the whole thing. So if I need to, maybe your final, it could be, it could be your final, it could be, I'll give you a header all in bits. Bits, all bits. All right? And I'll tell you, read it for me. So you're going to go and hear the first, you're going to tell me what's the version. You're going to read this for, you're going to tell me what is the header length. Surface type, you're going to tell me what, if there is a map for it. The total length, I'll give it to you in a bit, 16 bits in here. You'll be able to read it, right? Right? So now you have the map. You are able to read the header down to the bits. All right? Down to the bits. And every other protocol in this field, the same thing. It's like a map. It's designed in a certain way that you'll be able to read it. And that's what computers do. When they receive the packet, what they do? They interpret everything in here. Then they will have an action. Right? Okay, that's exactly what is a protocol. All right, and I'm taking my time to explain this thing, because later on when I explain the TCP, for example, or UDP, or I'm gonna go very fast. All right, because back then you're smart enough to go read in details and figure out the map. Okay, and here I'm teaching you addition. All right, but when I teach you multiplication, it will be very fast, because what is multiplication? Is like repeated addition. All right, so I'll take my time to teach you subtraction and addition. When we go to division and multiplication, I will go very fast. All right, so in here I'm just trying to give you a full example how protocol work, and I'm sure that you're enjoying it. Okay, it's like very nicely designed. Okay, usually I think about the networks, the way how they built it, It's really fascinating. It's really fascinating. Okay, it's like in a way it's like how human communicate. There's protocols, just they could design the protocols. How these machines they made these Ethernet cards, these network cards, these computers like really human, and they made the language. Okay, how they understand, how they interpret different things and all that. Fascinating. It's unbelievable. It's really I enjoy reading this stuff and trying to figure it out, right? So in an IP packet, the value of here, what is this? Header length. It's in hexadecimal 5. How much? 5 hexadecimal. That means how much in binary and how much in decimal? 5 in hexadecimal. How much is in decimal? Come on.
Five.
5 in hexadecimal. How much is it in decimal? 5. 5 and 5, right? So decimal, binary, decimal and hexadecimal, 1 is 1, 2 is 2, 3 is 3, 9 is 9, 10 is A, B is 11, and so on and so forth. All right. So don't get you confused in here. All right. So it's like it. Okay. So the value of the total length is okay. The value of total length, okay, is this one. So okay. So this 516 in 16 equals 5 in decimal, right? So 28. All right. In 16, how much is it in decimal? And that's very easy. So 2 in here, that means 16 and 16. Then we have the 8, right? How much is this? 40, right? So in here is 40. Here we go. So the header size is 5. However, the whole packet is 40. So what is the size of real data? So to calculate the header size is 5 times 4. How much? 20. All right. So remember that we have like this, right? So what we have in here, header. We are telling you it's 20. Okay. All right. And we are telling you the whole thing from here to here is how much? 40. So how much is the data in here? The data?
20.
20. 20 plus 20 gives you 40. All right. Simple. So in here it tells you the H length is 5. That means 5 times 4, 20. Then the whole thing is 40. So how much is the data? Real data is 20. 20 plus 20, 40. All right. You see how much, how much I have fun. I will have so much fun writing your final. Okay, how many things I could come up with, ask you to just to calculate. All right. Just the rules. You know the rules, you'll be able to understand anything. You know what is the size of, what the version of the IP, what is the length, you will know so many details. Even if I give you the whole packet in bits like this, 0 1 0 1 1 0 0. If I give you like 200 bits, all right, you'll be able to understand it. And by the way, machines understand only what? Binary. Binary. Okay, everything is in binary. All right. I mean, why you are using decimal and hexadecimal in our explanation? Why? For you and I to understand. All right. So, I mean, and the computers are digital, binary, right? And not even binary before it goes in the wire. When it goes to the wire, what it is? Current. Current signals. All right. 0 will be represented by a signal and 1 will be represented by other signal, right? All what we're doing in here is just for you and I to be able to understand it, all right? But everything in the computer will be binary. Let's take one more example. An IP in here, an IP packet has arrived with the first few hexadecimal digitals as shown below. All right. So, okay, this is the first. So, hexadecimal. So, how we represent, how many bits is the hexadecimal? So, the four, how many bits is the four? The four, how many bits? I mean, this is like ABC digital design. Okay, so how many? So you have the hexadecimal from 1, okay, to where? To 16,
Yeah.
right? Okay, is that correct?
No, 15.
So it's from 0
0.
to 15, right? Good, somebody's awake with me today. So 15, it's what?
F.
F. F.
F, sorry.
And 0, okay, 0 to F. All right. So how many bits I need to represent the 15? How I write 15 in binary? 1, 1, 1, 1. How much is this?
15.
And how we write this in binary? 0, 0, 0, 0. So each hexadecimal in here, how many bits?
8.
4.
4.
4.
8. 4.
Okay, each one is 4. So this is 4 bits, 4 bits, 4 bits, 4 bits, right? So for example, in here, this is the first 4 bits. What will give you?
In binary? 0, 1, 0, 0, 0. Yes.
Okay, in our header, let's go back. Let me refresh your memory. So the first 4 bits, where is it?
Virgin.
I'll give you in here what?
Virgin.
Virgin. So in here 4, right? It's in hexadecimal, which is 4 in here. Let me go in here. 4. So what is a virgin?
4.
4. 4. So the next 4 bits give you 5. So what does this next 4 bits will give you?
Length.
The header length. How much is the header length?
4 times 4.
5 times 4, which is equal 20. 20. Great. All right. So now, so this is the first 8 bits. What are the next 8 bits, if you remember? Okay. So the next 8 bits, these ones, what are these? This is the surface type. All right. If you take a look. And then the next here, the next ones in here. So this is 4 bit, right? Okay, this is 8, right? And this is another 8. This is how much? 16. Then we have 16 bits. What is this? The total length of the whole packet, 28, right? Okay. Okay, so this is okay. Then after that, in here, then the next 32 bits are for what? So okay, this is 8 plus 8, right? 16, all right? Plus 8 plus 8 up to here. So this is how many? Let me count. 1, 2, 3, 4, 5, 6, 7, 8. 8 times 4, how much? 32.
32.
So this is for the fragmentation information, right? Then the next 8 bits for what? Time to live, right? Okay. Then the next 8 for what? For the protocol. For the protocol use, right? And so on and so forth. So in here, they're giving you the hexadecimal. They are not giving it to you in the binary, right? In the hexadecimal. So the IP packet has arrived with the first few hexadecimal digits as follows. How many hops can this packet travel before being dropped? Which one determines how many hops it could travel?
Last 2.
What was the variable? What we call it? Time to live, right?
Time to.
So where is time to live? It's in here. So what's the value for time to live?
0, 1.
1. That means it will only allow to travel 1 hop. All right. So to find the time to live field, we skip 8 bytes, 16 hexadecimal digits. The time to live field is the 9th byte. This is the 9th byte in here. All right, which is 01. This means the packet can travel only one hop. The protocol field is the next byte, which is in here. There's a protocol field, 02, the 02 in here, all right? Which means that the upper layer protocol is IGMB. Let's go back. When it's 02, what's the protocol? Is IGMB, all right? IGMP, all right? Right? So it can't be any easier than this. You agree? All right. So let's talk a little bit about fragmentation. Let's talk a little bit about the fragmentation. All right. All right. So now, from the header, you'll be able to interpret everything. So a datagram can travel through different networks. Each router decapsulates the IP. So whenever it goes from a place, let's say you have a router in here, okay, and there is a source in here, and let's say you have a destination. All right, it's gonna keep. Let's say we have another router in here, okay, then it goes to the destination in here. So what will happen? You'll have a packet with an IP with a packet which has a header and body. You're gonna go to the router. It will decapsulate it. So each router will decapsulate the IP datagram, okay, from the frame it receives. Then it processes it. What does it process it? It's gonna read the source address. It's gonna read the destination address. It's gonna read the protocol version, and whether it's 4 or 6. It's gonna the header length. It's gonna read the data length. It's gonna read all the information, right? So it will decapsulate it, then it will process it, and then encapsulate it in another frame. All right, all right. It's like in another frame, right? Think about it like this. All right. So you're buying a gift for your wife or your husband. All right, and you are ordering it from where? And let's skip the husband and wife. You're buying it for your mother or your dad, right? So you order it from Amazon. The Amazon will send it to you inside a box. Let's say that you are buying your mom a new iPhone, right? So it's coming from Amazon with a box, right? Encapsulated in the box. Are you going to take the same box, send it to your mom? Nope. You're gonna open it, right? Open it. You're gonna write a card, include it with the iPhone, and then after that you're gonna put it in a new box. And the one came from Amazon. It has the source address is Amazon warehouse, and the destination address is your house. Now you received it, right? So what you're gonna do? You're gonna open it and you're gonna put it in a new box. And let's say that your mother lives in San Diego, California. Nice weather, nice place. You're stuck in Connecticut, cold weather. That's fine. You'll grow out of it. But you know what you're gonna do? You're gonna get another box, maybe a beautiful box, and you're gonna put the source address. Now, what is the source address? Is your address. What is the destination address? Okay, all right. You understand? So so encapsulate. So the each router receive it will open the packet, will read it like we were doing right now. Okay. Oh, this is the header. Okay, this is the information. This is the source address. This is the destination address. Oh, then it will encapsulate it again, and so that's a function of the router. So the router will encapsulate it another frame. It will put it in another frame. The format. Okay, remember in the frame level, and by the way, I said something wrong. Anybody captured that or no? I said that we change the source IP address and the destination. We don't. Source IP address will I mean, start to end will be the same. What changes? What gets changed?
Destination address.
The physical address, the MAC address, right? Okay, remember that the MAC address is from each link, right? But for IP, it's gonna go all the way to the destination, right? So anyway, so the format and the size, so you're gonna take a look at the format, the size of the received frame, depending on the protocol used by the physical network. All right, so it's gonna go from IP, gonna go to Ethernet. That's one scenario. You're gonna go to ATM. That's another scenario. You're gonna go to token ring. That's a different scenario. You know, okay. So the layer 2 protocols are different. All right. So it's gonna go through that. All right. So the format and the size in the frame depends on the protocol used in the physical network through which is going to travel. All right. So that means, okay, that means depending on the protocol used in the layer, we will know what is the minimum size and what is the maximum size for what? For what? Help me out. For what? Minimum size and for what?
Data. Frame.
For the frame. Okay? So remember in layer 3 we don't call it a frame. What we call it? Datagram. We call it datagram, right? So
Yeah, data.
okay, so in the second layer we call it a frame. All right, and the frame size depends on the technology used, right? So there's something that we need to worry about, which is like, the maximum transfer unit. What is the maximum transfer unit? Usually in IP is like 1500, for example. All right. So just an example. So let's say that the packet is 3000. Okay. So what we have to do with this, we have to divide it into. All right. Just I'm giving you rough. Okay. So again, let me draw it in here. So in here, let's go in here like that. Okay. And in here, for example, the physical. Okay. The data link layer. And in here we have the network, right? Okay. So let's say in this layer, the frame is the maximum is 1500. Okay, but I'm receiving packet in here, the packet in here. What is the maximum size for this packet in here? How much? How much? 64K, right? Remember? 64K, which is like 65 something, 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 right? All right. So let's say that we have the maximum. So how it has to be fragmented so much. So this is 64K and this is 1.5K. So how many fragments we're gonna need? 64 divided by 1.5, rough estimate in here. So how many? Too many fragments. Too many fragments, right? That's the whole idea. So that's what will happen, all right? Okay, because of the technology in here, okay, technology in here does not allow. Think about it like this is a highway, all right, a highway like this, all right, a highway, and then you are getting to a smaller highway, and the size of the car is like this, coming. Could this go in here? It can. So what we have to do, we have to divide it. This we call it fragmentation. All right, fragmentation. All right, so you have to fragment the data. All right, so here you have the IP datagram, as you see in here. This is the IP datagram. All right, and it's gonna go to the frame. Okay, so this is layer 2, and remember this is layer 3, right? This is the header, and the maximum length of data that can be encapsulated in the frame is the maximum MTU. All right, and then you have that trailer. All right, so that's exactly what you're gonna do. Only data in a datagram is fragmented. Only the data. All right. Remember, when you go back in here in the datagram, we have two parts, right? You have the header and you have the data. So what you're gonna do to fragment it, you're gonna create header 1, okay, like this, with data, with a portion of the data. Okay, then the same header, okay, with the other portion of the data, right? Okay, so the header will stay, in every subheader, and every fragment will be there. What will change? The data will be fragmented, divided, will be divided. right? So only the data on the data frame will be here. Okay, so do you understand what's the problem now? Just I want to make sure that you understood the problem. All right. So the problem is if a router connects a LAN to WAN, it receives the frame in the LAN format and sends the frame on the WAN format, different formats, right? So each network has something called MTU or maximum transfer unit. So each data link which is in here, I draw it in here, data link in here, each data link layer, okay, protocol has its own frame format in the most protocols. One of the fields defined in the format is the maximum size of the data field. What is the maximum size of the data field? In other words, when a datagram is encapsulated in this frame, the total size of the datagram must be less than the maximum size. Okay? All right. So that's exactly what we are talking about. So the value of the MTU differs from one physical network protocol to another. They are different technologies, different physical networks. Okay. So example, in the Ethernet LAN, how much is the MTU? The Ethernet LAN technology is 1500, like I put it in here. All right. That means, okay, that means if we are having in here, where is it? Let me clear this for a sec. Okay. So if this is like Ethernet in here, okay, if this is like Ethernet, so what is the maximum size for this? 1500. Okay, if it's Ethernet. All right. If it's like FDDI, which is the 5 bar, okay, the maximum will be different. The maximum will be 4,352, much more bigger. Okay, bytes. How about if it's a point-to-point or PPP protocol? It will be only 296 bytes. So it depends on the technology used in here in the protocol. All right. So in order to make the IP packet, which is in here, to go through this, we have to divide the packet. Okay, so we have to make, if we need to make it independent of the physical network, so we have to, to make the maximum length of the IP datagram equal, okay, to 65 or 64K. All right, so what we need to do, fragmentation. So the source usually does not fragment the IP packet. Okay, the transport layer will instead segment the data into a size that can accommodate the IP and the data link layer. Okay, all right. All right, so how the fragments is done now. Okay, so we know what we need to do. Okay, only data and the datagram is fragmented. All right, so in here D, do not fragment M, more fragments. So let's take a break and we'll come after the break.